right, we'll just wait a minute and then I'll make a few announcements. All right, so the next homework assignment having to do with some momentum applications, that's due on Monday. Ordinarily, remember that our assignments would be due before class on either a Tuesday or a Thursday, but you've got some additional time for this homework number 10. If you submit it Monday before noon, then it'll be counted on time. And then the second midterm exam we're going to have on Tuesday the 17th of November. That's the exam that's covering chapters 4, 5, and 6 of the book. And the timing of that test will be the same as the first exam, where it's released on Blackboard, available for you to download at 10:30 a.m., and then you need to submit it no later than 12:30 p.m. And if you email me the exam at 12:31 p.m., I'll just delete your email. So leave yourself enough time to upload it to MU to Blackboard. I expect that the typical student will probably need about 45 minutes to solve these problems. Students who understand the material really well and naturally work quickly may finish it as fast as 25 minutes. And then students who haven't been keeping up with the material or who've not maybe been doing the in-class exercises or solving the homework problems with much independent thought, they may not have enough time no matter how much was given. So if you want to go back through any of the recordings, then it's lectures 13 through 24 that this test is based on. And it's all going to be problem solving. There won't be any short answer questions. It's all problem solving on this one. And if you want to review the equation sheet in advance, it's the same equation sheet that you had accessible to you during the first exam. It's posted now on Blackboard, and you can also use your textbook or your previous homework assignments, and it's not allowed, however, to communicate with anyone else, including other students, during the test. So you should what you should submit is exclusively your own work. So before we go any further, are there any questions related to these announcements? Okay, so we have a couple of additional applications that we're going to talk about today with fluid momentum. This is going to be tying together the rest of Chapter 6. Next week's lecture on Thursday, since of course we won't have a lecture on Tuesday due to the exam, next week's lecture we get into Chapter 7, which is all about the energy equation. And so that's where we finally break free of some of the troubling assumptions that we've employed while using Bernoulli's equation, for example. But today's applications, nozzle and hovercraft, are both kind of interesting considerations having to do with fluid momentum. And just to refresh our memory about applying the momentum equation, let's consider a momentum problem that's occurring in two different dimensions. In this case, we have water that's entering some sort of a black box. And it's a black box. What we say is we don't really know necessarily what's going on inside. There must be some sort of a series of veins or pipe unions where the flow is being combined and redirected. But we don't have to necessarily know what's going on inside of the black box. All we have to do is draw a control surface around it to encompass the changes that are happening inside, and through the analysis applying the momentum equation, then we'll know the forces required to hold the system steady. And that's what this problem is asking. This says, neglecting gravity, then what force is required to hold the black box in place? So what you can see is that there are two fluid streams coming in. Stream 2 and stream 4 are both liquid jets that are entering this black box. And it's not water. It says in the problem statement there that this fluid has a specific gravity of 2.0. So that means that it's twice as dense as water. Well, what we do know is the volumetric flow rate of stream 4 and the velocity of stream 4, as well as the volumetric flow rate and velocity of stream 2. And so what we need to do is find the forces both in the x direction, horizontally, and also vertically, and find out what external force has to be applied to this black box to resist the forces that are imparted to the black box by the fluid jet. So we're going to be solving the momentum equation in both x and in y. I guess I could probably just paste it. If we were together in a room, what I'd do is write it on the whiteboard, but instead of that, allow me to just paste it on the screen here. Let's start by determining in the x direction what force is required, and then modify that same equation for the y direction. I'm sure I must have it written in terms of y among some of these notes. Well, if not, you know how to substitute a y for the x in the formula. So let me pause for a second and determine what force in the x direction has to be applied, and not just the magnitude, but also the direction. Are we pressing externally towards the right or towards the left? And then when we move on to the vertical forces, do we have to push up or push down on the box to hold it steady because of what's happening with these liquid jets? Figure out what forces are required to hold the system steady in x. So I will bring up the solution and we'll take a look at it together, and then maybe we'll talk about the vertical direction, but we won't yet begin going over the solution together because I'd like you to get the practice of solving that on your own. Just scrolling through an entire semester of notes here, trying to find our example, and I think I've got it. All right. So I've redone a sketch and shown that both fluid jets in the x direction are in. And so stream 4 is in to the right, stream 2 is in to the left. We know that stream 4 is 0.15 cubic meters per second with a velocity of 60, and stream 2 is 0.3 cubic meters per second with a velocity of 30. Okay, so in the x direction, here's our momentum equation. It's out minus in. Now both of these are in, so there's no out term. This first part of the momentum equation is just going to cancel out since the mass flow rate out is 0. And you can see that I've calculated the mass flow rate for 4 and for 2. And so it's our 2,000 kilogram per cubic meter density, since it tells us in the problem statement that the specific gravity, Sg, is 2.0. That means that compared to water, this is twice as dense. And so the density of this fluid is 2,000 kilograms per meter compared to the water density of 1,000 kilograms per cubic meter. So multiplying the density by the volumetric flow rate gives us how many kilograms per second is entering the black box through each stream. So the mass flow rate in at 2 is double the mass flow rate in at 4. But if we look at the simplified version of the momentum equation here, I've canceled out the outflow term, and we have each of the inflow terms. And pay special attention that the minus sign that's here in the equation applies equally to both of the inflow terms. And so there's the minus sign for stream 4. There's the minus sign for stream 2. And so when I start plugging in the numbers, I've got the minus sign and the 3,000 kilograms per second entering at 60 meters per second. And this is referring to stream 4, which is to the right, which is why it receives a positive value. But stream 2, since it's to the left, we have a negative sign for this one, which is moving at 30 meters per second to the left. And so that minus sign combines with this minus sign, and so 30 times 600 is going to be the same as 300 times 60, which means if we have a positive quantity and a negative quantity, they cancel out. And maybe you could have just seen that from the very beginning. You've got a jet going 60 with a volumetric flow rate of 0.15 and a jet that's going 30 with double the volumetric flow rate of the other stream. They're going to cancel each other out. So you could tell by inspection, but now you also know because you crunched the numbers on that, that in the x direction, the two streams cancel each other out. Okay, now, in the vertical, we know the flow rate at 4, that's given. We know the flow rate at 2, we know the flow rate at 1, but here at stream 3, there's no flow rate specified, just the velocity. So does that mean that we should just throw our hands up and quit the problem? Well, no, it doesn't mean that. It means that we're going to apply the continuity equation. Remember, in equals out. So inside that control volume, inside the black box, there's no capacity for storage over anything other than a very short period. You know, if it was initially empty, maybe it could fill up with water, but long-term steady state, no. You can't have an accumulation inside of that black box. So in equals out. So the inflow terms are the mass flow rate at 2 and the mass flow rate at 4. That's in. So if you add those together, then that should equal the outflow terms, which is the mass flow rate at 2 and the mass flow rate at 3. So in other words, I said in the chat box, m dot 3 equals m dot 2 plus m dot 4 minus m dot 1. So the other way to say that is the water that's going out at 3 is whatever water came in minus the water that went out at 1. So if it goes out through stream 1, it's not going to be exiting at 3. But anything that came in has to go out. And so it's either going out through 1 or through 3. And we already know how much is going through 1. So the remainder goes through stream 3. All right, so I'm going to pause again for a second, and that will give you some time to calculate what is the mass flow rate at 3 in terms of kilograms per second. And then finally, what is the force required to hold the system steady? And remember that we want to know the force and also the direction. So do we need to apply a force to the up or down to hold this steady when it comes to the vertical forces that are necessary to hold the system steady? Okay, let's look at the vertical here. We just finished the horizontal earlier and found that no force is required in the x direction, but that won't be true in the y direction because there's an imbalance in how much of the flow is going up versus going down. So in the y direction, we only have outflow. There's no inflow. And what that means is that we're going to cancel out this time the second term of the momentum equation. And so we can calculate the mass flow rate at 1 and the mass flow rate at 3. So 200 kilograms per second is coming out at 1. And so therefore, applying the continuity principle, in equals out, what that means is that stream 3 here at the bottom where we don't know the flow rate or the mass flow rate coming out, it's the in, so 2 plus 4, minus the other out, which is 1. So 2 plus 4 minus 1 means that 700 kilograms per second is going out down through stream 3. Now here's the momentum equation when we say that there's no inflow, so it's just the two outflow terms. And we're going to have to be sensitive to the magnitude of and direction of the velocities at 1 and 3. Since this velocity at 1 is up, it's going to be positive 20 meters per second when we substitute it into the equation. And then stream 3 is going down, so we will put minus 15 meters per second when we substitute that into the momentum equation. So you can see the mass flow rate times the velocity plus the other term, but here's the minus sign. And so that means that this stream at 3, which is going down, has a larger force magnitude than the upstream, and so then the net difference means that to hold the system steady we have to press down 6,500 newtons. And the way to think about that is just, there's all of this flow coming in, and what we know is that more of it is going down. And so there's a little bit going up, but more of it's going down. If you're going to be changing, if you're trying to bend that stream to get it go from sideways to down, you have to push on that stream to bend it down. In other words, to redirect it, an external force is going to have to be applied in the direction that you're trying to change the flow to. So you're trying to change a horizontal flow to a downward flow. You have to press down on that flow. And so that's what we find by substituting it into the equation with careful attention to the direction of these velocities. Any questions about either of the components of this example? I love giving problems like this on exams. If only we had an exam coming up sometime soon. And what would make it even more fun, you got to be honest, what would make this problem even more fun is if some of these streams were at an angle. Because right now it's just a little too easy. The inflows are both in the x direction. It would make things more interesting if one of them was at a skew, like coming in both the x direction and the y direction. I don't know, I'm just brainstorming there, but that's our black box problem. And if there aren't any questions, we'll move on to another. This time, though, we need to address the issue of nozzles. And here's what I'm going to tell you about nozzles. Is in this depiction, what we see is that there's a jet of water coming out of the nozzle. The little blue arrows and the fact that we don't have the solid black line anymore means that this nozzle terminates at a jet, and so the water is spraying out and it's not pressurized. After the water exits the nozzle and it's touching the air, it has a pressure of 0. But the flow at 1 is inside of a pipe. And in fact, the pipe continues. It's not shown. It continues off the page for some distance. But what we've done is we've drawn our control surface and we've cut the pipe so that we're just looking at a certain location. Let me draw. Oh, I have drawn that. How about that? So there is an external force that's applied because when we draw the control surface, there is a force on the outside of that pipe, and it is the pressure times the cross-sectional area of the pipe, and it acts as though it's an external force. And this is really complicated to think of because it's one continuous pipe, but with the control surface, what we are asking is, what are the external forces that are applied, and then also what is the force required to hold the system steady. So this is what you'd be given in a problem like this, but when you look at it, what you need to see for cutting a pipe, if you're cutting a pipe, not physically, but if you're cutting a pipe with a control surface, then what you need to see is this, where the problem is asking what external force needs to be applied to hold the system steady. So there's this flange that goes around the nozzle system. And the flange is where the force is applied to hold the system steady. Maybe there are bolts in that flange that are attached to the ceiling or some sort of a support and holding this whole system in place. Because what's happening is that the water comes into the control volume under pressure. There's a pump somewhere downstream or a tower, and it's pressurizing the water. But when we cut this pipe with our control surface, the water that's on the left side of our control surface is pressing on what's inside the system. What's in the system is inside the control surface here. So the pressure times area is acting as though it's one of the external forces. So here's our overall momentum equation in the x direction. It's saying the sum of the forces in x are the mass flow rate out times the mass flow rate out, velocity out in x, minus the mass flow rate in, velocity in x. So this sum of the forces in x has, in this problem, two different parts. It's got the pressure times area, which is acting as an external force, and then it also has the force that's acting to hold the system steady. So F sub x is what force you'd need to apply to hold the system steady. Now, on the right-hand side of the equation, then, you can see that I've combined the outflow and the inflow mass flow rate because it's the same. In this pipe, the mass flow rate that comes in and the mass flow rate that goes out is the same, and so I've factored that from this full momentum equation. So just I'm not differentiating between the mass flow rate out and the mass flow rate in any longer. There's just the mass flow rate, and then it's velocity out minus velocity in. Okay, so that's why you see P1A1. The units, if you multiply pressure by area, is going to be newtons. So there's this external force that's pressing to the right because the water is pressurized. So water flows through a nozzle at 0.3 cubic meters per second and discharges into the atmosphere. And we know both of the diameters. So even if you're a little fuzzy on exactly what to do next, if you're given the diameter for a circular pipe, odds are you're going to need the cross-sectional area. So it's a great idea to just calculate that at the top. And if you're given a volumetric flow rate of 0.3 cubic meters per second, you know it's water, you might as well calculate the mass flow rate from that, because that's what these formulas use, is m dot, and you were given the flow rate in a volumetric basis. So this is asking, determine the force required to hold the, determine the force required at the flange, so this F sub x. What is F sub x to hold the nozzle in place? Okay, so that's the given. Some of you may be wondering if there's some missing data. So here's the equation you're going to use. What data don't you have? Well, what about the velocities? How are you going to determine? The problem statement didn't say velocity. How are you going to find out what is V? Zach, any thoughts about that? How do you find out what is the velocity in this problem? Velocity out and velocity in. Or anyone, not just Zach? Since the velocity isn't given and we need it. All right, good. Khalid says V is Q divided by A, and he's exactly right. We do know the flow rate, so you're going to find V in by 0.3 cubic meters per second divided by A1, which you get from this given diameter, and then the V out will be the flow rate divided by the area at 2. So that's the continuity equation, is how you're going to find the velocity. Okay, so here's our equation. Is there anything else missing? We need to get the mass flow rate, and you do have what you need for that. And now Khalid has explained how you can get the velocities. There's one more thing that isn't defined yet. What's that? Oh man, virtual teaching is so bad. It's the worst. I don't know how you stand it. We don't know the pressure. P isn't given. Can you think of an equation that you might be able to use to determine what is the pressure in the pipe? Is there any equation that you've learned so far this semester that tells you about pressure change when velocity changes? I'm just going to sit here till somebody answers it. This will be a test of wills. What if Bernoulli Bernoulli's equation. Good. Thank you. We didn't have to wait very long. Well done. Yes, Bernoulli's equation. So, how does Bernoulli's equation apply here? Okay, well, there's location 2 and location 1. We want to know the pressure at 1. We do know the pressure at 2. Let me go get Bernoulli's equation. Earlier in the notes, the form of Bernoulli's equation that we're going to use here, I bet I can find it without too much trouble. It's the different version that I normally write. I normally write Bernoulli's equation in terms of head, but I think in this case it may be, since we want to find P, would be more advantageous if we use the form of Bernoulli's equation that's written in terms of pressure. Here it is. All right. Back we are. Okay, so we're going to use Bernoulli's equation to determine what is the pressure at 1. Let me get that down out of the top stuff. All right, so here I'm going to pause, and here's the suggested order that I think you should calculate things in. Find the areas. Find the area at 1, the area at 2. Find the velocity at 1 and the velocity at 2. And we're going to use a continuity equation for that. Then use Bernoulli's equation to find V1. Excuse me, P1. All right, so if you're taking notes, calculate areas, calculate velocities, then calculate the pressure at 1. And once you've done that, I think you can calculate the mass flow rate, and then everything substitutes in to this expanded version of the momentum equation where we have an external pressure force that applies. Okay, I'm going to pause for now and allow you some time to start crunching the numbers for this one. Okay, so you can see that the water that's coming in is having its velocity increase because we have convective acceleration. And so the velocity is going up. And the cross-sectional areas can be calculated from the given diameters, and we use those to determine both the velocity at 1, so 4.24 meters per second. It's moving pretty slow at 1, where we've got that big 0.3 meter diameter, and then at 2, where it's contracted down to 0.1 meter, then the velocity is 9 times higher because the diameter is 1/3. So the velocity is 38.2 meters per second. Now it's through Bernoulli's equation and substituting in the relationship of the changing velocity that we can determine the pressure at location 1, which is where that control surface is intersecting with a pressurized pipe. And so the water on the inside of the control surface is in our system. The water that's outside of the control surface and in the pipe pressing from the left to the right acts as though it's an external force. That's why we need to know the pressure in the pipe. So the pressure in the pipe is 720,000 newtons per meter squared. Now here we substitute in the momentum aspect of the problem. And there's both in and out in this momentum problem, and the mass flow rate's the same because it's not changing directions at all, it's not branching into multiple streams. So the mass flow rate's the same, but the velocity is different. And so part of the force that's applied is to resist the pressure times area effect, and then the other part of the pressure is because of the change in velocity. So you can see the respective magnitudes of those two forces. The part that has to do with changing the velocity is 10 kilonewtons to the right. If we just take a look at the picture again, if you're speeding up this fluid, if it's going from slow moving to fast moving, then you'll have to press to the right to resist that. In the same way that a firefighter who's holding on to a hose, when the water is going through the hose and spraying out really fast, the firefighter has to press forward to hold it steady. So that is the momentum part of this. But in this case, since there's so much pressure in the pipe, it's a really heavily pressurized pipe, then we also need to press in the opposite direction to resist that fluid pressure in the pipe that's outside of the system. And so that outweighs the momentum aspect of it. And so the force is going to be 40 kilonewtons to the left to hold the system steady. So here on the flange, the convention is to show f of x is to the right, but with the minus sign, and also by writing in text that the force must be applied to the left to hold the system steady, we've clearly addressed in the answer to the question that was asked initially by the problem is, what's the magnitude and direction required to hold the nozzle in place? Okay, so any questions about that? So if we're just looking at a couple of similar examples to what we've just solved, here's one where if there is a piston that's pushing on water and it's pressurizing the fluid inside of this pipe section, then the water would jet out through that. This is kind of like a syringe in a way. Then the external force required to hold the system steady would be some force that's applied by the pin to the pipe. And so in the case like this, we could use the momentum equation to find out, based on the force of the piston, you might be able to determine what's the pressure of the fluid inside of this pipe, because the force of the piston, for example, divided by some cross-sectional area will tell you the pressure of the fluid. And then the momentum equation, the sum of the forces in the x direction, would include the pressure and the area. So same thing here. If you know the areas, then you can find how the velocity is changing. And with Bernoulli's equation, you can understand the pressure at 1 if you know that the jet that's coming out, the water that exits through that nozzle, has a pressure of 0. And so you're starting with some location with the pressure being known, and you're determining the pressure inside of the pipe through Bernoulli's equation. Sometimes there are problems like this, where it's a union of 3 pipes coming in together. And so if 3 pipes are coming together, then you're drawing a control surface and you're cutting these pipes in multiple locations. This kind of curved shape just means that the pipe actually continues out of view, that it's not an actual physical cut or break in the pipe, but it's just we're drawing our control surfaces so that we can apply the momentum equation to what's going on inside of that control volume. And so if you're going to apply the momentum expression here, then there would be a pressure and area force acting to the right at 1, and then another one, even if the water's flowing out at 3. So you notice how Q3 is to the right and the water is going out. The pressure force acts from the right side to the left. So there's pressurized fluid and it's acting against the system. And so there's P1A1 that's to the right, and P3A3 is going from the right to the left. And then here at location 2, we've cut the pipe again, and so there will be a pressure and an area effect, and it's acting upward. And so P2A2, even though the water is going down, the pressure always goes against, it acts against the control surface that's cut the pipe. Okay, so let's move on to just one more practical application of fluid momentum, and that's the case of a landing craft air cushion. This is a really unique piece of military hardware, a hovercraft that's used to deliver tanks and armored vehicles and troops to beaches by the Navy and the Marines. And it's an enormous piece of equipment. It has a length of 26 meters long, a width of 14 meters, and it can displace, meaning it's the cargo and the weight of the vehicle itself, 185,000 kilograms. And in spite of that enormous weight, it can achieve speeds of approximately 80 miles per hour. So it's this big, heavy piece of equipment running on a cushion of air over the water and on the land. It can go up onto the land as well. And to do that, it requires an enormous amount of energy. It has a fuel burn rate of 1,000 gallons per hour. And so if you think your truck burns a lot of gas, this LCAC has it beat for sure. It can take 180 troops, 4 light armor vehicles, or a tank. So let's take a look at a video of this landing craft air cushion. And I sent you a PDF file a little bit before class started. You're going to need to take a look at that. I'll bring it up on the screen as well. But let me pause the recording. It's a video where they're going super fast. I think that would be fun to see a video of it going 80 miles an hour. But it's pretty impressive the way, it's just resting on its supports, and then suddenly it pops up when they start putting that air cushion underneath, and then they're using fluid momentum to steer it, coming out of these ducts on the top. You can kind of watch as they rotate around, as they're doing different maneuvers, they're rotating those ducts around, and then that causes the LCAC to rotate and steer. So, it doesn't spin on a dime. It doesn't have a rudder down into the water. It's just, it's using fluid momentum to steer it, as well as for propulsion, as well as for floating. And you may wonder what happens if, if it runs out of gas, does it sink? But no, it will float. It has buoyancy. So if you run out of gas, or if the turbine breaks, it's not going to sink, but it's sure not going to go very fast if it's not riding on that cushion of air. Okay, so what I emailed you was some questions that we're going to go through just to consider based on the specifications that were provided. What is the acceleration that can be achieved by that LCAC based on its weight, based on the amount of air that's being pushed around, and so on. So starting off, though, just to understand the concepts here, what I suggest is that you begin by drawing a sketch of the hovercraft, and where is the control surface, for example, where is the fluid coming in, where is the fluid going out. Just try and draw like a conceptual sketch, what force would need to be applied to hold the system steady, and so on. And then we'll start crunching some numbers here where we want to calculate the air pressure if you know the weight, the mass of the hovercraft, and you're going to need to calculate the weight from the mass. And given the dimensions, that's a top view dimension. So if you're looking at it from above, 26.4 meters is its length, 14.3 meters is its width. So let me pause for a second and give you a chance to both draw your sketch and then calculate. You maybe would think it's a huge amount of pressure to be able to lift. There's a tank there, right? To be able to lift a tank, you may think, wow, it must really be an enormous pressure. You must have to have a big air pressure in the skirt underneath of that, in the space under that rubber skirt. But it's not actually going to be that much pressure, a lot less than you'd expect. And we'll talk about why that is. All right, so start the calculations. Okay, so the little sketch that I drew, don't hold your hopes up for anything good. I'm about the worst artist that was ever born. Here we go. All right. Oh boy, that's even worse than I remembered. All right, so we've got this box with an engine inside, and it's forcing air downward. So that's what supports the weight, is the pressure times area force that's pushing up. and then the flow of air out, this mass flow rate times velocity, is what causes its forward propulsion. And if you were going to hold the system steady and solve for the momentum equation, then the F would be this force that's acting to resist the forward motion that's caused by the hovercraft's propulsion. All right, now what about the pressure? So we've got a certain mass, 185,000 kilograms, and we want to know what is its weight. So 1.8 million newtons is the weight of that. And there's a really big area though. So the area of 26 meters by 14 meters means that the area underneath that rubber skirt is 377 square meters. So in terms of the pressure is only 4,800 newtons per meter squared. And so just for perspective, that's 0.7 psi. So think about your tires, how pressurized they are. Most people will pressurize their tires to about 32 psi, and you wouldn't even be able to notice a change in 0.7 psi if you're using one of those little tire pressure gauges. But that's all the pressure that has to be maintained underneath that rubber skirt in order to lift up a fully loaded LCAC. So that's kind of interesting. It's all because it's such a big area. All right. So calculate the total forward thrust of an LCAC if it has two propellers. Each have a diameter of 3.6 meters, and then we're assuming that the air density of 1.2 kilograms per meter squared. The velocity off the propeller is 150 meters per second. All right, so we want to know the velocity of the air is given as 150 meters, but we want to know the mass flow rate. So remember, mass flow rate is volumetric flow rate, A times V, multiplied by density. So this is asking, what's the m dot? And then put the m dot into the momentum equation to find out the forward thrust. Okay, so let's look at the forces here. The area of the air. So the propeller is rotating with some diameter of 3.6 meters. That's awfully tall, but I looked up the specifications and I think that's right. So there's this stream of air going out from each of those propellers and has an area of 10 square meters. And the volumetric flow rate is the 150 meters per second times the cross-sectional area. So there's just a huge torrent of air passing out of each one of those propellers. And then if you multiply it by the density of the air, it's essentially moving 1.8 tons of air per second through each of the fans, which is why partly it's so thirsty for fuel. It's burning 1,000 gallons of jet fuel an hour. So 1832 kilograms per second each. And so then the force, since we're assuming that its maximum acceleration will occur when it has not yet achieved any forward velocity. It'll accelerate quickest at first, but then as it begins moving, the incoming velocity is going to reduce its effective forward thrust. And so the maximum force is going to be when the mass flow rate in and velocity in are zero, and it's only the out of the air that's being pushed by the propellers that causes the thrust force. So the mass flow rate of 1832 kilograms per second and the velocity means that it's 274,000 newtons of thrust each. So in total, that's essentially 550,000 newtons of thrust. And so last question, how quickly can accelerate? We apply F equals ma to determine that. So F equals ma means we want to find the acceleration. We're going to divide the thrust force by the mass of this whole thing. And it can accelerate at 2.97 meters per second, which is about 0.3 Gs. And that's initially, at least. Once it starts speeding up and the incoming air velocity is non-zero, then that'll reduce its effective thrust. But it's a very powerful vehicle and just kind of another kind of fun application of momentum. Any questions about this before we wrap up for today? All right, well, I guess that means I've got a test to write. We're having an exam on Tuesday. So you have homework to finish. I've got an exam to write. And if you have any questions as you're studying, feel free to get in touch. You can send me an email over the weekend, or you can give me a call on Teams, and I'll pick up anytime I'm able. And I'm usually in my office, definitely during office hours. So that's it for today. I hope you're doing well, and we'll have the exam on Tuesday and then another virtual class meeting on Thursday. Take care, everybody.